So first of all, the level 3 question. We let a be negative square root of 3 plus square root of 5, negative square root of 3 plus square root of 5 plus square root of 7. And then also we let b be square root of 3 minus root 5 plus root 7, and c be root 3 plus root 5 minus root 7. And so what we want to find is a to the fourth divided by a minus b times a minus c, and then plus b to the fourth times b minus c times b minus a times c minus b. So that's what we want to find. And so first of all, we can put all of these fractions over a common denominator. And so to do that, we just multiply them by the missing term. So this is just equal to a to the fourth times b minus c plus b to the fourth times c minus a plus c to the fourth times a minus b divided by a minus b times b minus c times c minus b. Yeah. And so that's how. And so next we just expand everything, and so this becomes a to the fourth b minus a b to the fourth plus b to the fourth c minus b c to the fourth plus c to the fourth a minus c a to the fourth. And it's all divided by a minus b times b minus c times c minus c. And so now what we really want to do is be able to factor out something from the numerator. And so in order to do so, we want to factor the numerator. And so the reason for this is just because that makes it, hopefully, it can cancel out with stuff in the denominator. And so we really just want to see if any of these are root of the numerator here. So the way we check this is by setting, a equals b equals c, and c equals a. And so if we do the first way, then this whole thing, then the whole numerator just simplifies to a to the fifth minus a to the fifth minus a to the fourth c plus a c to the fourth plus a to the fourth c minus a c to the fourth. And that's just 0. And similarly, if b equals c or c equals a, the ending result is still 0. And so what this means is that this is a factor of this. Oh, sorry. Yeah. Okay, now that's right. And so we can, if we do the division, we can see that this is just equal to a minus b times b minus c times c minus a times a squared plus b squared plus c squared plus ab plus bc plus ca, all divided by a minus b times b minus c times c minus a. And so these all cancel out, and so the remaining is just, what's left behind is just a squared plus b squared plus c squared plus ab plus bc plus ca. And so this is clearly just 1/2 of 2a squared plus 2b squared plus 2c squared plus 2ab plus 2bc plus 2ca. And so now we can recognize this, or for whatever reason, we can turn this into a plus b squared plus b plus c squared b plus c squared plus c plus a squared, all divided by 2. And so now we can substitute a plus b. And so the sum of these two numbers is, we can see is just 2 root 7 squared plus b plus c here is, as we can see, 2 root 3 squared, and finally c plus a, as we can see here, is just 2 root 5. And we square this, and so all divided by 2. And so this is 4 times 7 over 2 plus 4 times 3 over 2 plus 4 times 5 over 2. And so this just simplifies to exactly 30. And so the answer to this question is just 30. So does anyone have any questions about this problem? Okay, well, I guess not. And in that case, let's move on to this problem. So now this one. So either prove or disprove that for each positive integer n greater than 1, the remainder upon dividing 2 to the power of 2 to the power of n by 2 to the power of n minus 1 is a power of 4. And so actually, we claim that this is actually false. And so now, excuse me for a second. Okay, sorry. Yeah. So first of all, clearly, so now in order to find a counterexample, so first we'll work with just the assumption that this is false. And one common way to do this, one common way to solve these kinds of problems in general is just to like first assume that it's false, and then if you can't prove it, then see if you can prove that it's true. Because generally the way to prove that something is false is quite similar to the way to proving something is true. And so we know that, so clearly 2 to the n is congruent to 1 mod 2 to the power of n minus 1. And this holds for any n. And so in addition, we also have that for any integer k, we can see that 2 to the power of 2 to the power of n is congruent to 2 to the power of 2n minus kn mod 2 to the n minus 1. Yeah. And so we let 2 to the power of n be congruent to m mod n. And so clearly m is less than n, and n is greater than 1, so n is at least 2. And so that means that 2 to the power of n minus 1 must be greater than 2 to the power of n. Because the only way this will be false is when n equals 1 or 0. But neither of these conditions is true, because n is at least 2. Assuming, of course, that m is less than n. And so that means that the remainder in the question stated here, remainder is is equal to 2 to the power of n. And so what that means is in order to show that this is false, we would need that 2 to the power of m mod 2 to the n minus 1 is an odd, an odd power of 2 for some n. And so if it's an odd power of 2, then since the powers of 4 are in the form 2 to the power of 2n for integers n, then it's impossible for 2 to the power of m to be a power of 4. And so that would prove that the problem is false. And so, first of all, so one way to start is by letting n equal p squared for an odd prime. And so clearly the tangent function, which we'll just write like this, of p squared is just p squared minus p. And that's just because of one of the definitions of the tangent function. Or you can just use the fact that the only numbers that are not relatively prime to p squared are the multiples of p, and there are obviously p multiples of p from 1 to p squared. Okay. And so since 2 is relatively prime to p squared, that would mean that 2 to the power of 5p squared is congruent to 1 mod p squared. And this is just the Euler's tangent formula, tangent theorem. Or, yeah, I believe that was what it was called. And so what that would mean is that 2 to the power of p squared, 2 to the power of p to the power of 2 is congruent to 2 to the power of p squared minus p plus p, which is congruent to 2 to the power of p mod p squared. And so, once again, just since we wanted 2 to the power of m to be an odd power of p, then we want m to be an odd number. And since m, and so this is congruent to m. And so that means that as long as 2 to the power of p mod p squared is odd, then this is the counter. And so in order to do this, we can let p be equal to 5. And so when p is 5, 2 to the power of p is 32, which is 7 mod 25. And so that means that m is odd. And so that means that 2 to the power of m is an odd power of p for some n. And so that would imply that this is not a power of 4. And that's just because it's impossible for an odd power of 2 to be a power of 4, because the powers of 4 are the even powers of 2. And if we want to check, then you can see that 2 to the 25 is congruent to 7 mod 25. And so 2 to the power 25 is 2 to the 7 mod 2 to the power 25 minus 1. And this is definitely a possible mod remainder, mod 2 to the 25 minus 1. And since 2 to the 7 or 128 is not a power of 4, this is the counterexample that we want. So if n is equal to 25, we have a counterexample. All right. So does anyone have any questions for this problem? All right. Well, it doesn't seem like it. So, Calvin, are there any questions that you got that you want to answer uh, to the whole everyone in the meeting? Okay. Well, I guess she doesn't, and so that means that that's it for today's class. And so next week Friday, our guest speakers will be Michelle Wei and Catherine Lee will go continue going over her programming challenge problems, except that it will be weekly now. And Zachary Chung will continue going over the weekly physics challenge problems. And so thank you for coming, and I hope you have a nice weekend.